Hello everyone, I am Manoj and today we'll be doing the quantum bomb problem. So I've shared the link for this particular notebook on the group. Can you just quickly go load it up? Right, and please run the first cell that installs all the libraries you'll need. Right, so while that happens, I'll quickly walk you through the problem statement. So the problem statement is this: you are given a box. Inside the box is a bomb. The bomb is armed with a small photosensor. It's a light sensitive device, so if you shine any light on it, it triggers the bomb and the bomb explodes. Now the task is, this is a hidden box, like you don't know what's inside. So given this box, how do you detect a bomb inside? So classically you'd have to do some sort of measurement on it, take an X-ray perhaps, but anything you do with the bomb classically will eventually end up triggering the bomb and it'll explode. So there is no way you can detect the bomb without exploding it in a classical sense. But using quantum mechanics, can you do anything at all that lets you know that there's a bomb without exploding the bomb? So what you can do here is a pretty cool experiment that's described here. It's called the Elitzer-Weidman quantum bomb tester, and how it works is that you have a single photon source. It gives out photons that passes through a beam splitter. It just splits the beam into two different beams. Now for a single photon, when you have a beam splitter like this, and if your photons are coherent enough per se, it gives you a superposition of two states. So your photon can either end up going up or going to the right, but you don't know which one. So it's in a quantum superposition here. And now you have a mirror on top, another mirror here, a second beam splitter here. So your photon goes here and out. And you have two detectors that detect which way it ended up going. Right, so that's the situation being described here. So the way you can encode this whole problem statement into a quantum circuit is, you give it a state 0 as an input. The first beam splitter puts it into a superposition of 0 and 1, and then you send 0 through an upper path, you send 1 through a lower path, and if there happens to be a bomb, it will interact and it will explode. But we look into a case where you can actually detect it without exploding the bomb. First, let's work out the case where there is no bomb. Right, if there is no bomb, the second beam just passes straight through. Both the beams combine near the detectors, and it just so happens that one of the two beams outside the second beam splitter interact deconstructively. What that means is that the amplitude for that wave function will be 0. So if you work out the math for this, it works out like this. So this is your input state. Your first beam splitter can be represented by a Hadamard gate. What a Hadamard gate does to a 0 state is it puts it into an equal superposition of 0 and 1. So this is how we are describing a first beam splitter. Now the 0 state is representing the paths taken above, and the 1 state is representing the paths taken through the bomb. Now when there is no bomb, nothing happens. They just pass through, they go to the second beam splitter, and now you pass it through the second beam splitter. The second beam splitter takes this, and now you can work out this thing again, and it happens to be So now you can see that here the ones cancel out. You end up with 0 perfectly back again. So what's happening here is that there's destructive interference happening for one of the two detectors. So one of the detectors lights up, the other one doesn't, in the case where there's no bomb. So if you have to code this up, we represent it through a circuit like this. So you have a 0 state, goes through a Hadamard. This is where your bomb would have been, but since there's no bomb in this case, we just let that be there. Second beam splitter, which is the second Hadamard, and then you measure at the end. That's your detector. So let's code this up real quick. Is everyone running the notebook? Perfect. Yeah?
What is the second beam splitter? If there's 2 photons coming back.
Right. So the second beam splitter gives you that interference we require. So let's say there's the single photon got split into 2 parts. It's an equal superposition of both the parts right now. And when the wave functions combine here, it ends up destructively interfering at one of the parts and constructively interfering on the other part. So if there is a bomb, this detector lights up for sure, and this one does not. So that's how we are making use of the second beam splitter as an interferometer here. Right, here you that's your first beam splitter. And that's your second beam splitter. You just oops. Oh yeah, my bad. You got to run the imports first. Yep, and that is your bomb detector circuit. So the first Hadamard acts as your first beam splitter, the second one is your second beam splitter, and then you measure at the end. And if you actually run this circuit now, this cell lets you run it. Oh, was this not the notebook I shared? Oh, okay. So in the notebook I shared, these 2 cells have been commented out. So that is, if you want, these 2 lines are for you to run it on hardware, which we'll do it later. But right now, let's just run it on the simulator to see what happens. So this is a simulator. Yeah, it's fine. Yeah, and these are the results. So you can see that it reads out 0. One of the detectors has gone off with a 100% probability, the other one hasn't gone off at all. So this is the case where there's no bomb. You can see that there's constructive interference happening for one of the detectors, the other one destructively interferes out, so only one of the detectors lights up, and that's how you determine that there is a bomb. Now in the case that there is a bomb, wait, Shruti, there's no math in this one. Can you open the link I sent? The math in this one doesn't load. I had corrected this in a few other notebooks. Can you open the link I shared on WhatsApp? No, this one's.
That is the one.
Oh.
Oh.
Okay, yeah, this one is.
Okay, I was wait.
Yeah, this one. Okay, yeah, this is the right notebook. Let me code it up again. Right, so this is the circuit that we saw before. Now you right, so this is what you saw before. In the case that there is no bomb, you definitely get an answer of 0. But what if there is a bomb? Now what happens? So now your single photon comes here, it gets split into 2 different paths with this beam splitter, but when it comes here, it has to make a choice. Now this photon in superposition is interacting with the trigger inside. When you have a quantum superposition and you have an external system interacting with it, that is similar to what you call a measurement. All measurements are interactions in some sense, right? So now your photon is forced to make a choice. It should either be available on the top path, or it should make itself clear that it's in the bottom path. So you have a 50% chance that your single photon chooses the 0 path, or you have a 50% chance that it chooses the 1 state. And now if it chooses the 1 state, it definitely passes through the trigger is enabled, your bomb explodes. But if it passes through the other one, it passes through here. Now when it goes through the interferometer again, this beam is not available because it has definitely chosen the above path and there's nothing happening in the lower path at all now. So this single beam goes through the interferometer, there is no constructive destructive interference happening, and now it has another superposition going on here. So it's the same case that was happening here. You have one beam coming in, it's split into 2. Now there's no interference happening here, so you again have one beam coming in, it splits into 2, and now you have a 50% chance of either detector going off. So in the case that a bomb is there, you are effectively doing 2 measurements. The first measurement happens at the bomb. You either choose the upper path or the lower path, and the second measurement happens on the interferometer, the detectors after the second interferometer. Now if you look at the probabilities of all these happening, the probability of it choosing an upper path is 50%, it chooses the state, and then when it passes through the second interferometer, you end up with this. And now when you try to detect it, you either end up with at the detector at 50% again, or you end up with 1 at 50% again. So when I say 0 and 1 for the detectors, I mean this for this detector going off, I'll call this D1 as in the notebook, this is D2. So 0 again represents D1 going off and 1 represents D2 going off. So there's a 50% chance it chooses the upper path, and within that there are again equal probabilities of either detector going off. But in the other case where the bomb does go off, your whole setup is blown, and let's just say the qubit stays in this, so detector 2 will go off in this case. Everything clear with the circuit now? So now we'll try to encode this into a quantum circuit. Right, you have your qubit again comes in, goes through your first beam splitter, and it's put into superposition. Now you make your first measurement, and this is a measurement that happens at the location of the bomb. If this measurement returns a 0, you go ahead with your circuit, and if it returns a 1, you detect an explosion. You have two classical channels to record your measurements. We'll call them M0, M1, and you write what you detect onto M0. So M0 is holding the status of detection. If M0 is 0, the bomb did not explode. And if it's 1, you have an explosion. Okay, and then if it is, now let's assume that there was no explosion, it goes on as is. So now it's in a 0 state. You pass through your second beam splitter, you do your measurement again, and this writes to M1. It writes its results to M1. And now M1 has a 50% chance of being equal to 0 or 1. Right, as we saw. But then what happens in the case that an explosion does happen? In the case that an explosion does happen, we want our qubit to stay in the state 1. So we need to somehow remove the second interferometer, because that's the case where your setup blows away. How we do that is, we try to add a conditional gate before Hadamard that like sort of neutralizes this Hadamard. So you add an inverse to the Hadamard. Can anyone tell me what the inverse of a Hadamard gate is? The Hadamard itself. So now you add a conditional Hadamard here. And this Hadamard is conditioned upon a detection being detected, explosion being detected. Then you have your second measurement. Right, and this is your circuit. So what's happening here is that if there's no explosion, it goes through the second detector, the second interferometer, the second beam splitter, my bad, and passes through a different measurement. But in the case that there is an explosion, your setup is blown away and your qubit stays in a 1 state. Yeah? Right, so that's the point. So once the setup explodes, you don't have any measurement or anything, but you're sure that your qubit was in the 1 state before the explosion, because that's what caused the explosion. So we'll just let it stay in the 1 state. And that is the reason we are adding this second Hadamard, because if we detect an explosion, it means that there was a 1 here. And if there was a 1 here, we want it to stay as a 1 without passing through this Hadamard. So we add Hadamards inverse before that. So what's happening is that if there is an explosion, it stays as 1 and you will measure a 1 at the end. Does that answer your question? Right, exactly. There is no interferometer, but you know that it was at a state of 1 before. Right? So in the case that there is no explosion, it went up here, it went through this, and then you are able to say that it went through one of the 2 detectors. But in the case that there is an explosion, it implies that the single photon took the lower path. So from that you can infer that it was at a state of 1. And that is what you are trying to encode through that circuit, that if there is an explosion, the final output you should get has to be 1 no matter what is happening in between. And that is what we do by adding that conditional Hadamard. So if there is an explosion, this conditional Hadamard just neutralizes this part of the circuit and you end up with 1 at the final detector no matter what. Cool? Right. So let's code that up now. Your first beam splitter is the same thing as before. And then you perform your first measurement. Right, so you're measuring the first qubit and then you're writing it down to 0. This is what will represent by M0 there, and that records the status of your bomb exploding or not. Then you have this thing called an if test, and what it does is you can code in conditional gates here. So you can choose to implement your gate or not conditioned on what this classical register says, and the test is if classical register 0 says 1. Right, so if classical register 0 reads 1, you add a second hard mark. Oops. Right, so you have to fill your code in 3 different places. First one is instantiating the quantum circuit here. Then you add your first Adamant here. You include the case for a measurement here, and then you add your second Adamant here. Once you're done with all that, it should run. It did not, and there's a colon missing. Yeah, and this is your circuit in the case that a bomb is present. So if a bomb is detected, this conditional Hadamard neutralizes this Hadamard, and your end result will end up being 1 no matter what. Now let's run the circuit, but before that, can you guys tell me the probabilities of different cases? You have M1, M0. They can take, these are 2 classical bits. Each one is 0 or 1. So end up with 4 possible combinations: 0, 0, 0, 1, 1, 0, and 1, 1. Can you tell me what's the expected probability of each of these 4? Okay. The second one? Huh? 25? Okay. Third one? Yes? What do you guys say? Come on, someone take a guess. 25? You see, we added this second Hadamard so that if there is an explosion, this one has to measure 1 no matter what. Right. So this will be 0, and this has to be 50%. So this is because we conditioned this Hadamard based on this. So if this is a 1, there is no more operation happening, so the other one will be locked onto a 1, and this one is saying if a bomb has exploded, you measure a 0, which is not possible because of the entire conditional Hadamard setup. We can't go in there. Huh? Yeah? No, there's a 50% chance your beams, the photon can choose to go on the upper path also. Yeah. Right, no, the setup only explodes in 50% of the cases. So your source gives out a photon. The photon can choose to go up or go to the right. If it goes up, you have a further 50% splitting. But in the other 50% chance that it goes through the setup, now it explodes. So there's a 50% chance of it exploding, a 50% chance of it not exploding. Oh, is it? Oh, okay. Let me just switch these two. All good? And that is what you see. Right, you have 50% for 1 0, sorry, for 25% for 1 0, 25% for 0 0, and 50% for 1 1. Now let's just look at what just happened. So in the case that a result comes out to be 0 0, it's the same as the no bomb case, right? Your detectors read 0 0 and there was no explosion. So there's no way to say that if you get this output that there was a bomb inside or not. So this one reads inconclusive. Okay, what if you get this output? Your bomb did not explode, but you got a 1. You could not get a 1 in the case that there was no bomb, so you are sure that a bomb is there. So you say a bomb was detected. And in this case, an explosion happened. An explosion can only happen when the bomb is there, so obviously a bomb was there. So in the case a bomb was there, with a 25% chance you could detect that a bomb was there without exploding the bomb. Now this is interesting because in the classical case you had to explode the bomb no matter what to detect if the bomb was there or not. So by using this quantum superposition, you can actually figure out without destroying a bomb that if it was there in the first place or not. And this is something called interaction free measurements that you can look up more on. But this is one particular case where you use a Hadamard to give equal splitting up there in that and that those two positions. Can we do any better than 25%? 1 0. So in the case that a bomb wasn't there, what would this read? It definitely has to be 0, right? Because there is constructive destructive interference happening for 1. So if your second detector reads a 0 and no explosion happened, it could either mean that there was no bomb at all, or there was a bomb and it happened to be this case. So you can't say if a bomb was there in the box or not conclusively. So that's why this is an inconclusive case. But if you end up with a 1 in this measurement, that 1 is not possible if there was no bomb in the box, right? So if there's a 1 in this measurement, it has to mean that a bomb was there and you managed to detect the bomb without exploding it, which is good, and you did that by 25%. But if a bomb explodes and that happens with 50% chance, then you still have detected it, but now you just bombed out your whole setup. So can we do any better than this 25% limit? And turns out you can actually, and this is through something called the quantum Zeno effect. So if you guys have heard of this idiom, a watched pot never boils. So if you are looking at a pot of boiling water and if you just stand there waiting for it to boil over, it takes forever to boil. And if you look away for a second, in a second it just boils off. So this thing in a quantum sense is called the quantum Zeno effect, where if you try to make repeated measurements on a quantum system, it cannot evolve freely. So let's say on a Bloch sphere, you start out over here this is 0. What should be the state at the other end? 1, right. So now you have some process that takes you from qubit 0 to qubit 1. What process takes you from qubit 0 to qubit 1 passing through the x-axis? X gate. Right. So that takes you passing through the y-axis, it takes you to the 1 state. That's the x gate. But let's say there is some process that takes a finite amount of time to go from here to here, and you can actually map out the path it takes on the Bloch sphere. Now once the path is here, I make a measurement. Now once I make a measurement, I either force it to take one of the two states, 0 or 1. What's it more likely to take in that case? 0, because it's close to 0. And if I say the angle was, okay, never mind. So now it has a very high probability of going back to 0 and an extremely small probability of actually collapsing to 1. It's not 0, but it's very small. Now it goes back here, then again it starts evolving along the path, and I make a measurement again, it collapses back to 0, starts evolving again, and I keep doing this over and over again. What I'm essentially doing here is I'm able to preserve this quantum state into the state 0 by making repeated multiple measurements. So by measuring the state again and again, I'm able to hold on the evolution of the state. This is called the quantum Zeno effect, and we'll try to do something similar to, yeah, come on. You don't necessarily destroy it, you push the state into one of the available stationary states. So every state is a superposition of possible stationary states, and if you are making a measurement, let's say in the z basis, your stationary states happen to be 0 and 1. So when I make a measurement in the z basis, it forces a quantum state to align itself with either 0 or 1. If I am measuring with, let's say, the x basis, the stationary states for an x basis are plus and minus. These are what you get by acting Hadamard. So h of 0 is plus, h of 1 is minus. So these are stationary states of the x basis. So if I measure in the x basis, it will either force it to take on either 0 or 1. So when we say it destroys the quantum state, we actually mean it destroys any possible superposition that the quantum system has. But it's still a quantum system, like it can evolve freely after that also. So this is something we did in the previous circuit, right? Why not? So let's say I put my quantum state in some sort of field where it is constantly interacting with the environment. So at any point it will start evolving, and I can just force it back, but it will not stop evolving, it will just keep on trying to do the same. It's like if you have a ball on top of a hill, it always wants to roll down. I always pick it up, put it back up there, but it will still want to roll down. It won't stop rolling down just because it's at the top of the hill. So it's a similar analogy here. And you can look at this, we did the same thing here, right? We measured a qubit in the middle of its operation, and we still treated it as a qubit after that. Measurement doesn't necessarily mean it stops being a qubit, just means that it can't have any superposition after the measurement, right? Immediately after that. Okay, now how do we use this to improve our odds of detecting a bomb? Now let's say instead of using a Hadamard, we end up using the R gate, the rotation along the Y basis. Right. So what this does is, for any qubit on the Bloch sphere, it rotates it about the y-axis by an angle theta. Right. So if you act this on the vector 0, can you tell me what the output is? Right. So you end up with So you are still putting your qubit into a superposition by using this gate, but now by tweaking this theta parameter, you can tune how much of it has to go into 0 and how much of it has to go into 1. So in the case where theta was pi by 2, what would you get? 50-50. Right, that was your previous case. You had 1 by root 2 1. This is what you had. But now we can actually play around with theta and come up with different systems that give us different odds. So now our modified circuit works like this. You start with the 0 state, you act the R gate on it to get a superposition, you pass it through the bomb circuit, and then you repeat that n times. So let's say you choose theta to be pi by n. Measurements are meaningless because there's no setup anymore.
But if you have a run like after that, then we look at how
Do you know that?
after run,
Right.
so in any experiment, if you get one and after there are some measurements, in that case,
Not necessarily. The 1 after all these zeros only shows up in the case that you have some interference that they don't come back properly. So in the case that there was no bomb, right, all of these would perfectly merge back together, pass through the RY gate multiple times, and you end up with a measurement 1 at the end.
if there is no problem, this state 1 will be registered, but after that, immediately come back to 1.
No, so you'll have to do multiple iterations, right? Each of these intermediate measurements won't happen in the case that there's no bomb. The bomb is what's causing all these measurements. In the case that there is no bomb, this measurement doesn't happen. You run the entire state through the RY gate multiple times, and the final measurement at the detectors that you make will give you a 1, right? But then in the case that a bomb is there, you make multiple intermediate measurements. These are telling you that the intermediate measurement results are 0 or 1. 0 corresponds to no explosion happening at that iteration. 1 corresponds to an explosion happening at that iteration. Okay, so one showing up at any of these places will tell you that an explosion happened. So if you run the circuit and get the results for this, right, so now we just ran the circuit, happening was 0.25. So that's the case you ended up with. I can't hear you, sorry. Here? Huh? Right, so if you choose an arbitrary n, the probability of getting n consecutive zeros is that, and the probability of getting 1 in any of these places will be just be 1 minus that. So if you choose a large enough n, the probability of getting all zeros will be much higher than probability of getting 1 in any of these places, and that's what we're seeing here. So the probability of explosion is 0 here, and the probability of that happening was 0.95 for n equal to 50. But for the case of n equal to 1, it has to pass through the bomb, and then you have a definite explosion there. So by altering your n, by making n larger, you're pushing down the probability of the bomb exploding. It doesn't definitely have to collapse to 0. So let's say it was at an angle alpha, the probability of collapsing back to 0 will be cos square alpha, and the probability of collapsing back to 0 will be this, alpha by 2. Right, it will either collapse back to 0 or it can collapse back to 1 with a certain probability, but since this state is much closer to 0, it has a higher probability of collapsing to 0 than 1. Right, so from one of these. So let's say it collapsed back to 1 by a very small chance. The chance of that happening is small but non-zero. So if it ended up collapsing down here, it will start evolving from here according to that particular dynamics again. So what you're trying to do is you're trying to hold off the state at that location without evolving with a certain probability. Right. No, so in the case where there was no bomb, the measurement doesn't happen at all. Okay, so in the case that there was no bomb, it will go from here, it will move to this position. If there was a bomb, it would force a measurement and it will collapse back to one of these two cases. But when there is no bomb, there is no measurement. So it keeps evolving all the way until it reaches 1 down here. But if there was a bomb, it has a probability of collapsing back to 0 and a much smaller probability of coming back to 1, in which case there is an explosion. So you can see that by keeping theta very small, you have a much higher probability of it going back to 0 than going back to 1. So that's how you end up with no explosion. Any other questions there? Right. So your photon, when it passes through the first beam splitter, can either choose to go in the upper path or the lower path with probability is 50%. And we have two classical wires, right? We call them M0 and M1. M0 stored the first measurement of it going in the upper path or the lower path. So if M0 was 0 at the end, it tells you that there is no explosion happening, or if M0 was a 1, it tells you that an explosion happened. So M0 can take up two values, either 0 or 1. Now if M0 is 0, it means that a single photon took the upper path and it passes through the second beam splitter. But now when there was no bomb, it just happened that the second beam would interfere with the first beam. You would end up with a definitive answer of this state. But now the second beam is not there, so this splits again by a 50% chance and you end up with these two cases. And this is the case where your bomb does go off, and the case where you have 0, 1 is not possible because your photon, if it chooses to go in the lower path, it's stuck in the lower path, it can't go back to a 0 path. So this state doesn't show up in any of the results. Yeah. Questions? Good. Perfect. Thank you. I hope you had a lot to take away from this, and this is one of the many interesting paradoxes in quantum mechanics, where you would expect a bomb has to definitely go off based on your classical intuition, but it doesn't, just by harnessing a few key quantum properties here. Thank you.